So the momentum is the generator of translations. What is the generator of a rotation going to be? We can try and guess that by looking once again at dimensional analysis. So our transformation is going to be a rotation that's going to be a function of some angle, which doesn't have any dimensions. And because if I have rotations around a fixed axis, then they're additive. In other words, if I rotate by a certain angle and then I rotate by some other angle, I can just add the angles together and that will give me my net rotation. Then this must be the form of an exponential of the angle times the generator. So this is the generator of rotations. And what we're going to do is we're going to look at the units. It obviously has units of h bar, and that's units of angular momentum. And that is indeed the answer. And again, this is actually a definition of angular momentum. So when we take our axes and we rotate everything around by a certain angle around a certain axis, that gives us the angular momentum. Now in fact, we've got an implied axis here. So in general, we don't just have, just like we did with translations, we don't just have one coordinate, we actually have more than one coordinate. And the normal way to describe that is we describe our rotations as having some unit vector, which will be our axis, and some angle. Now I know I'm using J for the total angular momentum. That's the definition of the total angular momentum. And this again is the projection of these three operators. There's a Jx, a Jy, and a Jz. And this is just the dot product with those three. So this gives us a particular generator for a particular axis, and then this gives us the angle. There's actually a very interesting point that we have this vector operator here, and there's terminology here that can be very confusing, so let's go over that very carefully and slowly. A vector operator is using the word vector in a very different sense than we've been using it so far in quantum mechanics. It's actually the old-fashioned sense. Here we have a vector being a physical direction in physical space. A vector operator is talking about a triplet of operators, three operators. And those three operators are in a particular list, and they somehow describe an x component spatially, a y component spatially, and a z component spatially. But we've got two vector spaces here. We've got R3, that's our space, and we've also got our Hilbert space. And our Hilbert space, describing our quantum system, can be very large and it can be very strange. And these two spaces are different. And we talk about vectors. Our state is described by a vector in Hilbert space, and our spatial vectors. And they both have the word vector in, and that's what's likely to confuse you. But a vector operator is a triplet of operators that somehow transform just like vectors do. Remember when we were talking back about vectors and tensors, they're geometrical objects. And so they have some physical meaning besides just the fact that there are three objects. When we were talking about vectors before, we were talking about three numbers. And not just any three numbers gives you a vector. Three numbers can describe a vector, but in general, a vector is something that if you rotate your coordinates, your vector has to rotate. So those numbers have to change. So those numbers were just representations of something else, of something physical and real. And in a sense, that's what these things are supposed to be as well. So these three operators are representatives of observables of particular physical directions. And so therefore, if we change our coordinates, if we change what directions we're talking about, then we have to change these operators as well. And so a vector operator is a triplet of operators that when we say rotate our coordinates, we're going to have to change those operators in a standard way. And in fact, to define that standard way, we're just going to use rotations. So a vector operator is a triplet of operators whose components transform as vectors do under rotations. And we'll go into detail about that a little more in next week's lectures.